Hello viewers, welcome to this video lecture series on analysis and design of algorithm. In this session I shall continue with the previous topic, that is asymptotic notations. The last type of notation is the theta notation. So let me explain this theta notation with an example. So once again I have kept the previous content as it is. Now let us see what modification we have to do in order to understand this theta notation. So what I'll do is, first let me change the heading. It is theta notation. Okay, and now the first thing what we have to do is, theta notation represents what? Big O notation represents the upper bound running time complexity of an algorithm. Omega represents the lower bound running time complexity of an algorithm, whereas theta notation represents the tight bound running time complexity of an algorithm. So what is this tight bound word? Once I explain you the concept, then you will be able to understand. Time being, just I will replace this lower with tight bound. And when it comes to definition, what is that how you have to define for theta? A function t of n is said to be in theta of g of n, denoted as t of n belonging to theta into g of n, if t of n is bounded both below and above, by some positive constant, multiples of g of n for all large n, that is, if there exist some positive constants c1 and c2 and some non-negative integer n0, such that, now this equation, how will you write for theta? Because there are two constants, so you have to write down like this: c2 into g of n less than or equal to t of n less than or equal to c1 into g of n for all n greater than or equal to n0. So what exactly is the definition? Whatever you wrote for the omega, which was representing the lower bound time complexity of an algorithm, this represents the tight bound, means in between, neither lower nor upper, in between. So you will be having here two constants, not just one, c1 and c2. So these two constants will be has to be greater than 0, c1 and c2, and for what value of n, that is, for what value of n, t of n will lie in between c2 into g of n and c1 into g of n. So the same thing we can understand with the help of a graph. Now it is not just one function in the graph, you have to show two functions. One is c1 into g of n and another is c2 into g of n. So what I'll do is, for the same graph, whatever I wrote earlier, I'll make this as c2, I'll make this as c2. So I need to put c1 is above t of n, so that one also I'll include here. This one is your c1 into g of n. So now for what value of n? So now the graph will appear in this manner. You have two functions, and what is the relation between these functions? c2 into t of n should be lesser than or equal to t of n, should be lesser than or equal to c1 into g of n. So as you see in the graph, t of n is now lying in between c1 and c2. So this one, the earlier one. So as you can see in the graph, these two functions, c1 of g of n is here and c2 into g of n is here, and in between is what, your t of n. So now in this case, what is that, you are going to represent the tight bound running time of an algorithm. So for what, given any example, for what values of c1 and c2 and for what value of n, this tn will lie in between these two, c1 and c2, in between these two functions. So now we need to check with an example. So we'll take the same example what we had taken for earlier cases also. Tn, given is tn, which is 2n plus 3. Given is g of n, which is n. Okay. Now here this is the equation for the theta notation. c2 and c1 we need to find out. In this case there are two constants. So since we have already worked with this example only for the upper bound and lower bound, for us it is easy to immediately set the values for c1 and c2. c1, what we had taken here is c1 5, and c2, which is here, this lower bound, we had taken c2 equal to 1. So now we'll take the same value, c2 as 1, here I am substituting, g of n is n, less than or equal to, t of n is 2n plus 3, less than or equal to, c1 is 5 and g of n is n. Now we have to see for what values. So we'll start with first n equal to 1. Okay. C1 equal to 5, C2 equal to 1 and n equal to 1. This one we are checking first for n equal to 1. So 1 into 1, 1, less than or equal to 2 into 1 plus 3, 5, less than or equal to 5. So when we have substituted n equal to 1, what is that we have observed? 1 is less than 5, yes, true. 1, 5 is equal to 5, it is true. So that means our n equal to 1 value holds good, but still we should not stop, we should take n equal to 2 also and check. Always remember, you have to check for some 4 values of n, keeping the same values of C1 and C2, so that we can see whether for that value of n onwards the functions are in this manner. So we'll take now n equal to 2, 1 into 2 is 2, less than or equal to 2 into 2, 4 plus 3, 7, less than or equal to 5 into 2, 10. 2 less than 7, yes, true. 7 less than 10, yes, true. Fine. So then we'll take n equal to 3, C1 is 5 and C2 is 1. Okay. N is 3, less than or equal to 2 into 3, 6 plus 3, 9, less than or equal to 5 into 3, 15. Yes, it is true. So that means whatever value we had started with n equal to 1, it is right. That means n0 is 1 now. From that 1 onwards, the C1 into g of n will be above t of n and C2 into g of n will be below t of n. So our final values are C1 equal to 5, C2 equal to 1 and n equal to n0 equal to 1. And definitely it is satisfying also. As per the definition, the constant should be greater than 0. Yes, it is greater than 0. And n0 should be greater than 1. Yes, it is greater than 1. N should be greater than or equal to n0. Yes, it is greater than or equal to n. So this is how you have to understand this theta notation. Given will be t of n and g of n. Then you need to find what is asked in the exam, whether they have asked you to find out the lower bound or upper bound or the tight bound, because in the question it will not be mentioned whether you have to use the equation for the big O notation or you have to use the equation for the omega notation or you have to use the equation for the theta notation. Simply it will be mentioned for a given value of Tn so and so, for a given value of Gn so and so, determine the lower bound running time complexity of an algorithm, determine the upper bound running time complexity of an algorithm, determine the tight bound running time complexity of an algorithm. So you use appropriately that equation, find out the correct constants, and for what value of n and constants the equation holds good, that you need to determine. So hope this session is useful to you all. If you find it useful, please like, share and subscribe to my channel. Thank you, bye bye and take care.